Not much. I just came up from underground 2 a.m. this morning.
From home stake?
Snow lab.
Oh, snow lab. That's right. You're a snow lab. Well, I stay above ground because at my age, when you go underground, you may not come up.
Well, you know, there's less of a gravitational field down there, so you'll age more slowly.
Thanks for the advice. I see Cabot Ann. I see.
Yeah, you missed your slide was in my talk this morning.
I know. How did you know I wasn't there?
Because I checked. Because I had to chair my own. I had to chair the session that I gave a talk in.
Oh, that's great. Jim Fast won't show his face.
I will. Hey, Frank.
There he is.
Good to see you, Frank. It's been a while.
Yeah, it's good to be seen and not viewed.
Looks like you're actually in a laboratory.
It is. It is. It's my special project, which I will announce someday.
I announced it this morning.
Which one?
Oh, is that not the small zone refiner?
No. The zone refiner's in another lab.
Oh, okay.
I know you announced it this morning.
Yeah.
No, this is top secret until I make it untop secret.
Okay, so you want to not move then. You have to stay right there. So you hide it.
It's a challenge.
This technique is so old, there isn't anybody on this call that will remember doing physics like this.
What's old is new.
So it looks like you're sitting in the middle of a winery there.
Well, a vineyard, but you know, yeah. You know, if you can get yourself outside in some way, this is the way to do it.
When people show these fancy outside shots, I look for the wind to make the trees move a little, and it never does.
Yeah, it's amazing weather we're having.
So is Susanna on it?
Yeah, I see her video.
Susanna.
Hello, how are you?
Hace mucho tiempo, ¿no? We see each other twice a year because I'm on the science committee of the Confranc Laboratory. And I have been working with Professor Fabienne since she was a student many years ago. It doesn't look like it could be many years ago, but it was.
Excellent. I figured I'd have a hard time finding people for this topic that you didn't know. But...
Okay, I stopped playing the sound when people join, so now you just have to look at the count if you want to see, but we're pretty much up to some reasonable number, so if you want to get going whenever you want. People will keep joining if last time is any indication, but I don't think we should wait for everyone.
Great. Let me see if I can open this properly for you. Okay, so welcome everybody. I wanted to just give a very short introduction. I'm going to have the four panelists today, who I'm very excited to have with us, introduce themselves and also introduce the technical aspects of the topic before we get into the discussion and talk about the collaboration aspects and the multidisciplinary aspects related to building that collaboration that was very successful. I think a lot of the focus will be on LEGEND, which is a nuclear physics experiment. So forgive me for not being high energy physics, but I think there's a lot of a lot of connection between the neutrinoless double beta decay experiments and the dark matter experiments. So with that, I will share my slides. Don't seem to be able to, oh, here we go. Okay, Susanna, if you want to introduce yourself.
Okay, first of all, thank you very much for your kind invitation to be here in the panel today. It's really a pleasure. So, well, my name is Susana Cebrián. I am a professor at the Faculty of Science of the University of Zaragoza in Spain, and also associate researcher at the Canfranc Underground Laboratory, which if you don't know, it's placed under the Pyrenees at the border between Spain and France. So I have developed there most of my research career. I work in the field of the investigation of rare event phenomena, in particular the direct detection of dark matter and the nuclear double beta decay, which is related to many interesting neutrino properties. I have worked with different types of detectors, but in most of the experiments, my work has been focused on the background studies and the low background techniques. So in this way, now I'm collaborating at the ANICE experiment in Canfranc, which is intended to confirm or refute the annual modulation observed by the Dama Libre experiment in Gran Sasso over more than 20 years. I think all of you know about this. I am collaborating also with Darkside, which is based on the Gran Sasso laboratory in Italy, but also in Canfranc there is some development related to detectors to quantify very low levels of argon-39. Also, I work for TREX DM, which is a project which is being commissioned in Canfranc to search specifically for low mass WIMPs using a high pressure TPC read by micromegas. And also, I collaborate in the radioassay of materials for the next experiment, which is what we heard yesterday about this experiment in the presentation by Ben Jones about the baryon tagging. It is a double beta decay experiment. And also for the YAXO observatory, which is a project to look for solar actions, which at least in the first step will be placed in DESI in Germany. Okay, so that's my brief introduction about myself. I think that working in the field of rare event searches, copper is extensively used thanks to the advantages, electrical, mechanical, and thermal properties for shielding, for mechanical structures in cryostats, cables. It's also very important that copper has a very good intrinsic radio purity. Probably surely much better than other metals like stainless steel, at least concerning the primordial isotopes from the uranium, thorium, and chains and potassium. But of course, if we are working for background-free experiments, radio purity can also be improved. And a particular issue, I think, for copper is the cosmogenic activation, that is the production of long-lived radioactive isotopes due to the exposure of materials to cosmic rays. In particular, cobalt-60, I think, could be the main cosmogenic product that we find in copper, and which is very relevant for many experiments, for many different searches. Of course, this cosmogenic activation can be, let's say, quite easily avoided if we just reduce the exposure to the cosmic rays. But to avoid this exposure, typically we need some measures which complicate the production of detectors and the preparation of the experiments. Of course, flights must be avoided. All the materials should be stored underground as soon as possible. Even in some cases, shieldings have been prepared, have been designed to protect the materials during the transportations from a company to the lab. To assess the real necessity of taking off these measures and to limit the residency time in surface, it would be desirable to have reliable tools to quantify this production of cosmogenic isotopes. So a lot of work is put on this, and this is in particular one of the topics where I have work especially. But cosmogenic isotopes are not the only issue. Of course, one must to take into consideration the surface contaminations which could be induced by the radon exposure, by the exposure to radon, which can plate out on the surfaces, leaving, for instance, lead 210 or these other isotopes. So also many work is on these. Different procedures are being studied based on chemical etching or electropolishing in order to reduce as much as possible this the radon surface contamination. Even I think that copper is in any case a very radio pure material, but one issue that I'm sure that we are going to comment on this in the panel is the problem of quantifying these low levels of radio purity. So also a lot of work is underway to develop very sensitive techniques and procedures based on ICP-MS, alpha spectrometry, to be able to quantify the activity in the copper, to check that the experiments have the required sensitivity. Sorry, Dieter, I think you are mute.
Thank you for that introduction. That was very nice. So that introduces us to the problem. And now I'd like to have Eric Hoppe introduce himself. Although I did want to mention the bullet point didn't make it. He's also the co-owner of the Heron Bluffs Winery and Vineyard, which you can see behind him there. But go ahead, Eric.
Well, thanks for that introduction slide, Jeter. I owe you a bottle of wine for the nice words. Yeah, I mean, I've been at PNNL now for over 3 decades, and I think there's kind of two eras here that I'll refer to, and I'll call it PM and AM. And I'm not talking about the clock, but I'm talking about prior to Majorana and after Majorana. I was going to call it before Majorana, but I didn't like the acronym. In any event, the reason I make that distinction is because we did a lot of work during the Majorana years to scale up the electroforming process and to develop the assay capability to measure the purity of the copper as well. So, so Jeter, if you'll go through the slides for me, I'm gonna take you on a quick kind of whirlwind view of electroforming, and it may be it's an oversimplification, and many of you probably know this, but it's good review perhaps. So, as Susanna said, I mean, the motivation is that copper can be made very pure, and it has good thermal and electrical properties. So, it's used in a lot of experiments. And these are, obviously neutrino-less double beta decay and dark matter searches. And, at some point we could determine, what purity we could make the material. We actually started developing assays back about 2010, and then that helped to inform development of the process that we started putting in place for Myrana. So you see this reference down here in 2015. That was one of our first publications on the assay that got us down to levels that were relevant to Myrana, which had a 0.3 microbecquerel per kilogram target, or something on the order of, single digit femtogram levels of uranium and thorium, for example. So let's go to the next slide. I should say the picture there is of some pre-Myrana copper that we did. So, just to go through this very quickly, copper has a reduction potential it's higher than most contaminants that we're concerned with. And so in the process of plating it out, if you're somewhat careful about the potential that you choose, you can exclude these other contaminants, and I list there, of course, the typical ones: uranium, thorium. You can actually exclude lead to a very high degree. Cobalt, which is an activate, as mentioned by Susanna, is a activation product, a cosmogenic activation, and so you want to exclude that when you're electroforming. And of course, you're trying to do that underground because you don't want to just activate at the same time that you're making the copper. So if you go to the next slide, so you'll see that basically we go through just an example here with uranium, which I mentioned before as a reduction potential of negative 1.8. When you compare that to copper of positive 0.34, you end up with a cell potential of negative 2 volts. So basically it says, well, copper being positive is now energetically favorable, and the reduction of uranium is just not going to happen as long as you don't turn up that voltage, something well above that setting. So, if you're plating at a 0.5 volt, you've pretty much excluded uranium. So go ahead to the next slide. So of course, it's not quite that simple, because if that were the case, then all commercial copper would be highly pure, right? So what I've talked about really is just the thermodynamic issues. There's kinetic and fluid dynamic considerations as well, that basically at some point, because of just the mass transport, you start pulling contaminants into the copper. So here I just show how we've addressed that. We use this pulse reverse plating technique, which basically plates here. You see about 60% of the duty cycle is spent on plating copper. And in the process of doing that, you draw in some of those contaminants. So then we have kind of a resting step. And then what we do is we reverse that polarity. So suddenly now, instead of plating onto this cathode, we turn it into the anode. And for about 20% of our time, we just dissolve that surface that we just plated. And what that allows us to do is, first off, level the surface so that we don't have a lot of a rough copper deposit. But it also allows those contaminants a chance to get off. They didn't want to be there in the first place. They got drawn in with all the copper ions, a flood of copper ions that were coming in. So we're just giving those an opportunity to come off and then mix back into the bulk solution. Let's go to the next slide, please. So that's really how we do that. We overcome some of those issues with that approach. And there's, of course, mixing of the bath and so on. Again, we're going to bring that bulk back into solution, or those contaminants back into the bulk we have to mix those back in so that they aren't right near the surface and we don't redeposit them again. So part of what informed that process is being able to develop, as I mentioned, some of the assay techniques. So here, I have a whole list of things here that we assay, but main reason for the slide is you see there at copper that we're able to electroform that and measure the purity of that at 0.01 ppt. And the slide's reloading. Okay. And so that was that ability to measure the purity of copper, and in this case also we did lead for that reference that you see there, was important to informing how we made some adjustments to the process to continue to improve the purity as well as the deposit as far as the physical properties. So what you see off here on to the right, I should point out, is you see a little proportional counter there that is a copper tube that a spring is being loaded into, and that's that top picture there is a bunch of those proportional counter tubes that have been plated and machined. So that's just one of the applications that we have is for copper. Let's go on to the next slide. And so along came Myrana, and we had to ask the question is how pure can we make copper, because the radio purity requirements were certainly much more stringent than any other experiment. And at the time, those who were involved will remember that we really didn't know. We didn't have assays that were adequate. And so in the process of developing that capability, we're able to actually look at things like, hey, what's the best commercial copper we can get out there? And here I'm referring to the Myrana assay paper. These are really the best commercial copper results that we've found to date, which I think says a lot for the effort that Myrana folks went to. I think I would say like Vince was very much involved in that, in coordinating with Arubis, was the vendor here, to get this to get material that was of this purity. And so it's really the best to this day of assays that we've had. Now, EXO 200 actually sourced their material from Arubis, and it's very similar to this level. So if you look at that assay paper, you'll find out that, I mean, that was again similar results, same vendor, and it's a real testament to that vendor's attention to detail and capability of making, tons and tons of copper and attaining this level of purity. But of course, Myrana needed to go much lower, and so our ICP-MS techniques that were developed, we assayed the electroform material, and that was made both here at PNNL and at SURF. We had 6 baths at PNNL and 10 of those in the temporary clean room, which a number of us remember with, I'm sure, with fond memories. But that material assayed to a point where even our newest capability of measuring uranium, thorium is the example here, we really couldn't see it. So you see indeterminate values there, but you also see that in parentheses, the microbecquerel per kilogram levels certainly met our target, or better than our target of 0.3. So we haven't had any real motivation to do much better than that, frankly, because nobody's asked us to do that yet. So let's go to the next slide. So I wanted to talk a little bit about not just bulk contamination of copper, but when we have surface contamination issues. So here we actually had some electroform copper. It was a thin foil. As you can see, there it is, positioned on the tray of an XIA alpha spectrometer. I think it's the 1800 alpha spec. And here you see the sample was laid out, and we basically, it was of course exposed to air and so on until we did our etch work that we published. And you see the reference here in 2007 to get a essentially below the level that spectrometer can measure, which is on the order of about, frankly, it's really about 5 or 10 nanobecquerels per square centimeter, or about 10 to the -4 disintegrations. Gosh, I'm trying to remember the units that they stated in. It's 10 to the -4 events per hour per square centimeter, I believe. So let's go to the next slide. So what happens if there's issues where, if I've got a bunch of commercial copper, I can't always electroform everything. So what do I do when I have issues with bulk copper contamination, lead-210, and I either have to go and electroform it, or what can I do? So we had a situation here with super CDMS where we were trying to get that surface contamination down really below, our target was 25 nanobecquerels per square centimeter of polonium. And you can see here we were well above that target as we kept measuring this commercial copper in hopes that we could eventually allow the polonium to decay from the surface. So, but you can see here we're, of course, as you expect, asymptotically approaching some level. If you go to the next slide, that level was around 100 nanobecquerels per square centimeter, which was still over a target. So one of the things we investigated was to take that commercial copper and just go ahead and put a layer of electroformed copper on that so that you attenuated that bulk. And then you'll notice that we get down to essentially the background of the instrument again. So there is application where if alpha is your main concern, you can use commercial copper, and then you can just play it over the top of it very cleanly. And we showed that you certainly meet well, somewhere we're measuring after a subtraction of 1 ± 8, which is basically a 0 number for that instrument. Let's go to the next slide. And those are just some examples about how you can, what you would use copper for, outside of what you might think of just the typical electroform application. And so one other I'll just bring up here, and then I think I'm done. We actually use our own copper to measure, to do polymer assays. We went to significant issue here, or effort to try and find material that was pure enough that we could ash polymers in, and we tried all kinds of things, every sapphire, and the list goes on. And we finally just decided, we're just going to make our own boats out of our electroformed copper. So what you see in this little diagram up here is that we electroform copper in a thin sheet. We peel that off of the mandrel. We make these small boats. We fill those with a polymer sample. That goes through then a tube furnace roasting step. And then you're left with these awful looking oxidized copper boats. But now you take the whole boat and you dissolve that, and then we run it through our copper cleanup step, and we do the assay on that. And we're able to get again down at 100 femtograms or less detection limit. We can go lower if we choose to, but it's easier for us to run. As you can see, the sample size there is a few hundred milligrams. And so So we can do this. This is, this takes us a few days, and it's an application for use of electroform copper, where we couldn't have done this assay prior to this to development of the copper, because there just wasn't material out there clean enough. So I didn't get too much into Myrana, but I wanted to pass that on to Cabanan, who I think is going to talk about that maybe a little more in depth. So I think I'm done. I'm ready to pass this off to her.
Okay. Thank you, Eric. That was a nice handoff to Cabanan. So I'll let you take it away, Cabanan.
All right, can you hear me? Sorry, I'm making, hopefully you can hear me, and then I'm trying to make the chat box go away. Okay,
yes,
so my name is Cabanan Christofferson. I actually was originally faculty at the South Dakota School of Mines and Technology. And if you're familiar with that, you see now on my slides, we actually went through a university rebranding this fall, and now we're known as South Dakota Mines. So that's the new logo that you'll see for reference to this university, which has been extremely beneficial, because since it is strictly an engineering and science university, we've had quite a nice pool of students that have had the opportunity to work on not only Myrana, but any of the R&D that is going forward with Legend 200 and now Legend 1000. And so by training, I am a chemist with a master's in material engineering, but that emphasis was actually in organic polymers. And so to be brought on to Myrana back in 2010, October of 2010, really was based off experience I had with previous job with Department of Defense in terms of lab infrastructure. So you can advance to the next slide. All right, so this was really just a pretty much a boilerplate slide that I've had for covering topics that I have for research. Eric put us all to shame with his lecture on electroform copper, but I'll fill in the blanks about what Myrana did and then where the electroform copper has gone from there with the development of Legend 200 and 1000. So I served under Eric as the deputy task leader for electroforming for Myrana, handling what most people know as the temporary clean room. I'll let you know that if you look at modern slides from SURF, they scratch that name, not liking to show that it was a temporary clean room. That it was referred to as the electroforming lab, which was decommissioned in April of 2016. So between the summer of 2011 and pretty much the spring of 2016, Myrana grew over 6,000 pounds of electroform copper on those 10 baths of various sizes, everywhere from about a 1 centimeter diameter up to the standard, what we call a shield mandrel at about 33 centimeters. So coming from Myrana, this also just expanded my involvement in terms of things like the low background production of clean techniques, because not only producing the copper for Myrana, which was fine in terms of large stock pieces that you can see, the assay developed by Eric at PNNL showed how clean we could create this bulk material. But Myrana really had to tackle the issue of how is it that you keep your copper clean when it's machined into everything as small as cable management pins or small screws and nuts that held the detectors within the cryostats. So that is a huge focus and huge thing that we tackled and showed that we could keep the material as clean as the bulk going forward. And that's really important for the development of Legend. So that also spans a little bit about understanding not only keeping polonium off, but the removal and reduction of the polonium and its daughters through plate out. So as you can see, besides all of the electroforming and basically handling all of the chemicals, as you mentioned, Jeter, John Wilkerson does a good job of not letting any of the physicists touch anything that has to do with chemistry. And so I've managed to handle all of that for them, which has served very nicely because since we have the wet lab at the Davis campus, we cleaned all of the pieces for Myrana and now continue to do that for other experiments. and all of it was also machined underground, and we still maintain that capability. So you want to go to the next slide? So going forward, now that MyRANA is really technically done in terms of construction, we are still taking data. And in fact, right now we are in the phase of taking data with the new ICPC detectors that will go into Legend 200 in the existing infrastructure of GERDA. So Legend 200 is actually under construction. We have detectors that are both over in GERDA. They've shut down and they now will be facilitated into Legend 200, but we're also running these detectors in the MyRANA setup under vacuum instead of in the liquid argon like GERDA did for the next setup. So I serve as the electroforming task lead for Legend 200 and on the technical council, along with some other chemistry-centric topics for the experiment. For Legend 1000, I'm a member of the project office and also now am the L2 for all of materials and assay for the extent of that experiment. And of course, we still are in the steps of putting together our conceptual design report. Oak Ridge has been selected as the lead lab for that, which makes sense since they were the lead lab for MyRANA. And then of course, the location is to be selected. I think I'm pretty much done. I think one of the things that I would like to highlight is going forward about understanding how it is handling is just as much, if not more important than the production of the clean materials. And this goes from everything from copper to even the plastics. We see that, you can start with the cleanest material, but through handling and machining, you can increase this background to a point that it's not acceptable for the experiments. And so that is a huge development in helping achieve the backgrounds of what Legend 1000 will need. And we've already shown that we can do this for Legend 200 through these techniques that we changed after what we learned in MyRANA, but it's going to be critical for the development with Legend 1000.
Okay, thank you, Kevin. Actually, the tip of the spear on this massive copper electroforming project.
By the way, you did point out that we wanted to talk about Legend, and there was an extra slide in my set I sent you that was the Legend overview.
So I didn't want to focus on the actual project itself because I think.
Okay, well, good. I was just wondering when you'd mentioned that, I was like, oh wait, there was a slide. So no, that's totally fine.
Thank you. Yes. So we'll get into the collaboration aspects of Legend. I really want to understand, how it came together. What were some of the challenges, both from, the scientific perspective and also from the funding perspective and the cultural perspective between, people coming from those different educational backgrounds. So, next, I want to introduce. So thank you again, Kevin. I wanted to introduce Frank, or have him introduce himself. We're delighted to have him here as one of the founders of this, or the leaders in this field. So please, Frank.
Okay, well, I don't think we want to look at this slide too long, but it's it's my pleasure to see a lot of my younger colleagues. I have a few stories that go way back. Some people may not want to hear them, but I certainly was the leader of IJEX. I led the U.S. contingent for Cuoricino and Cuore, which are bolometer double beta decay experiments. And with a few people at Duke University, we started MyRANA. I will get back to some of the things on this slide, but probably I would just like you to take it down. So my connection to PNNL was in 1979. In 1976, Ettore Fiorini from the University of Milano Bicocca and I met at Purdue University, where they had Neutrino 76. Fiorini and I decided to write a proposal to do double beta decay. He'd had done already the first experiment with germanium, and the first experiment where the source was also the detector. Beautiful series of experiments with natural germanium. We got shot down. We got wonderful reviews for the physics, for the ideas and this and that, but they said, you don't have a handle on the background. A few years later, Fred Reines, who was one of my mentors, told me, well, you know, Frank, there are these two guys out there in Washington State, a guy named Brodzinski and another fellow named Wogman, and you ought to visit them. And maybe you can learn something about how to do low background experiments. So I went out there, and Ron used to like to tell the story about, I had been in Washington, D.C. the week before, and without thinking, I looked at the map and I said, you know, Richland, Washington is further north than Washington, D.C., and it's cold as hell here. It may be really cold there. I got off the airplane in Richland, Washington, where we used to have service. And there's Ron standing there in a short sleeve shirt and sunglasses. It's a summer day practically, as happens in Richland sometimes. He loved to tell that story about a physicist who didn't know anything about the weather. Furthermore, one that was a naval officer. So I gave a series of talks, and I got Ron and Wogman interested, and they had already had some detectors inside, above ground. We didn't have an underground facility at PNNL at that time. It was PNL. It was Pacific Northwest, Battelle Pacific Northwest. And that's 40 years ago. So I told them, they looked at, that was their low background detector run by a fellow named Jim Reeves. How many people remember Jim Reeves? Well, he lived in Richland at that time. Now he's in Arkansas. And I think he still has his house in Richland, comes back. Jim was a technician with no academic background. He got uninvited to continue at the University of Arkansas and came out looking for a job, but he was one of the brightest guys when it came to technology. And I don't know if the people at PNNL remember this, but Jim Reeves, with my $25,000, made the first cryostats from electroforming copper. Now, we didn't know nearly as much as Eric does these days, but we sure did cut it down. And so we electroformed copper on steel mandrels, as is done today, for the first time. And I told him, I said, at $25,000 a piece, I won't be able to do 4 or 5 of these. So Jim moved the operation to his garage. And we made 6 more cryostats in his garage. So for $30,000, I was able to get a lot of cryostats. We did quite a bit of work. We published, we used the low background, above ground detector in the old area in PNL, the one they ripped down. And I was able to put a better bound on neutrinoless double beta decay of germanium-76 that had been ever done before. It was 1983, published in Physical Review Letters. That got their attention. So we started a project called IGEX, International Germanium Experiment. And this is called, my connection there was to put together a collaboration of Russians, Soviets, actually in those days, Spaniards, because I had a friend, Angel Morales, and I know Susana knew Angel very well. He was the chief professor there at Zaragoza, and Ron Brodzinski and company at PNNL. We produce good students with IGEX. Does anybody know Harry Miley? He was my student. Craig Alseth, he was my student. Juan Collar, he was my student, and maybe I hope he's behaving himself these days. And Todd Hosbach. All were PhD students of mine, not all from IGEX, but the 3 were. So we created the first, we built the first enriched germanium detectors. They were made. They were made in Oak Ridge, Tennessee, but the company that made them is no longer around. But now they moved some of those people over to Miriam, which was Canberra at one time. And I learned how to make detectors from Larry Darkin and the people that were making the detectors for us. And we created 3 large 2-kilogram detectors out of enriched material and 3 smaller ones first. One of the 3 large ones were the first enriched detectors in Gerda. They took them from Spain to Italy, and they after we were through with them. I think IJEX was really the father of my Rana. IJEX was finished. We had published a number of interesting papers. The first terrestrial search for dark matter was done by our group, with starring a lot of the actors of Pacific Northwest National Lab. That did not involve the Spanish team, but then we performed the first search for axions from the sun, where we collaborated with the people at SLAC and produced one of the earliest paper in that area. So things, one meeting that we had at Berkeley, there were 2 Spanish fellows. Now, for reasons I won't explain, I can speak Spanish. I'm Italian, but I can speak some Spanish. Maybe Susanna will tell you that it's not the best, but it's there. And I was walking down the street in Berkeley, and I heard these fellows speaking Spanish. Now, I learned a lot of my Spanish from Latin America. And I heard these fellows in the back, and I said, they're from Spain. I turned around, it was Angel and Julio Morales. And they said, oh, we heard your talk, and we would like to talk to you. So they were, at that time, involved in an experiment with the French, where it was what they tried to make a low background detector. They did put it inside of sodium iodide detectors, and the French claimed that they saw neutrinoless double beta decay of germanium-76 to the first excited 2+ state in selenium-76. No, that would be much a smaller probability than seeing it to the first 0+ state, a little bit higher. And of course, Morales and the team at Zaragoza said, no, this isn't right. There was a big fight in Germany over this, and they split up. The Spaniards and the French went their own ways. And Morales said, Frank, if you and Ron Brodzinski can produce a low background detector and put it in Canfranc, and I'll tell you what that was like. You put it in Canfranc, we can beat these guys and shut them up about having discovered neutrinoless double beta decay. So Ron and I went to work, and we did it. And I went over and installed the detector. And the funny story is that I flew it flew into Barcelona, and we got it on a truck and brought it over. Why did we need to put it on a truck? Because Brodzinski made a giant swimming pool. He had a very large wooden detector, a wooden box for this detector, and he had it plastic coated inside so that the snoot of the copper was down in the water, and they flew that whole thing. We got it to Canfranc, and we opened it up, and Morales turned to me and he said, Frank, we don't need to import water from the United States. We have plenty of it here. But it had gotten into the electronics. So Canfranc then was a railroad tunnel, and it was still a railroad tunnel, no trains, thank God. And these fellows had a little car with railroad wheels on the car, and it was a gasoline car, and they had put what we call a cassette that was like something you'd have at the beach, little trailer, and it had 2 rooms in it. And the deep room was where they put a lead shield and the detector. But you can't put a lead shield on a flimsy floor like that. So we cut a big hole in the floor and put the lead right down on the tracks. Started it there with wooden buffers. Built the shield and put this detector in there, and then used the low background lead we could find. And in very short order, we proved that the Spaniards were right, the French were wrong, and that was finished. But the ministry in Spain insisted that Morales do an experiment to disprove it for political reasons. So they did it. Then we started IJEX. After I was able to get the Soviets, I had to sell my soul to the Soviets to get this enriched material, which we got 18 kilograms of. And that involved a fellow named Pomansky from the INR and Kirpishnikov. Now, the people that have done work with Gerda know these, at least they know Kirpishnikov. He was in Gerda for a while with my other Russian colleagues that came from both the INR and the ITEP in Moscow. And we had a big fight about where to put the detectors. Well, the Homestake, we would start them off there. Okay, we put them in Homestake. Ray Davis gave us a laboratory. Or Baksan. If you've been to Baksan, you know that's way out in the middle of nowhere. And in Soviet times, sometimes you couldn't get much to eat there. But the director of the Baksan was our colleague, so maybe that wouldn't be so bad. But the Spain is sort of first of all, we didn't have much room in Spain. Morales went out and found some people for some kind of a price he could afford to make a laboratory. The laboratory, Susanna will remember, was the small one that we now call the small laboratory at Canfranc. It belonged to the University of Zaragoza, not to the new organization. We made IJEX there. We made the big detectors there. The smaller ones, because of the political will of the Soviets to want to have not only the scientists, but the politicians that wanted to have part of IJEX in Baksan. So I had to put them in Baksan, 3 of them, and I had to go to Baksan to install them. IJEX did fairly well. Craig Alseth was one of our shining stars in those days, learned a lot of electronics and started us off in being able to do pulse shape discrimination. We published the first paper in pulse shape discrimination in Neutrino 96 in Helsinki. And Craig played a major role there. We were able to actually, at the end of IJEX, we were able to actually get quite a bit of good data from about 1/5 of the amount of data they had at Heidelberg, Moscow. But they also later had very nice pulse shape discrimination. We got it first. And so based on that, we broke up after a while because there were some difficulties with the Russians. Pomansky later passed away and things were a little bit difficult. And so Morales and the Zaragoza team became far more interested in dark matter. He wrote review articles. Their people became experts in a number of ways of data analysis. They're a very, very sharp group in data analysis. And even though Susanna hasn't said this, we have a claim in Rome that they have seen dark matter. Well, the best experiment that is refuting this to a 2 sigma level is done by the Zaragoza people in Canfranc. It's called ANICE, and it's a beautiful experiment. And so they went off into more into dark matter, and I worked with them in dark matter. We did small dark matter germanium experiment for low threshold and that sort of thing. But then they settled on when the new Canfranc laboratory was built. I became the chair of the science committee in 2007, and then course, you may remember a large piece of rock fell, and that laboratory had to be rebuilt. So we found a director, and he led the Spanish team in rebuilding the laboratory, which is quite nice now, and with a lot of very good experiments in it. So after Majorana, the detectors were not going to be operated. So we maintained them in Canfranc until we would decide what to do with them. In the meantime, Gerda started up, and they started up with a large collaboration, a lot of Russian help with isotope and new types of detectors and things. So they asked us, the detectors weren't mine, they belonged to the Russians. The cryostats, however, were made at PNNL, and they were ours. So they're still in LNGS somewhere. But anyway, they took our first 3 big detectors, and all the way through Gerda, 2 of them operated very nicely. They rebuilt them a little bit. They operated very nicely, and we started then Majorana, and we went starting Majorana at Duke University with just 3 or 4 of us. And then we asked Harry Miley to be the spokesperson of Majorana. So we moved the whole thing, went back to PNNL, and we started with Majorana. Majorana actually was a dream of Brodzinski's a long time before that. We didn't call it Majorana, but it was called Banjo. It was a half a dozen detectors in a thing that looked like a banjo, and it's much like the thing you have underground at PNNL now, except you have two of these clamshells, and it never worked. We never were able to get a good vacuum on it. It never worked, and somehow we were able to then tell the agencies we're going to put them in individual detectors, which we did, but that was his dream to have a multi-detector system. So Majorana turned out to be that. Unfortunately, Ron passed away very quickly after lunch at a meeting. I could not go to that meeting. I was remarried from having been widowed, and I just had married Ann Braithwaite, and she had some minor surgery in her eyes, and I couldn't go to Vanderbilt where they were having that meeting, or near Vanderbilt, and he died very quickly. He had his pancreatic reaction, not cancer, but it was a pancreatitis that he'd had once before. Passed away, and we lost a lot. With Ron was a person that you could really depend on him. A lot of people thought he was a bit crazy. You could really depend on him to get things done, and he was an excellent organizer, and we lost that. But Harry took over, and Majorana started off. Then when it got large, of course, what moves in is the agencies. We've got to have somebody in one of the national laboratories manage this, because now this is going to be not a $3 or $5 million experiment. It's going to be $20 million. So get out of the way, folks. Well, at that point, I was hired back. I had been co-spokesman with Harry. Harry and I were sort of demoted. He left, and Craig left shortly after that. And I was going to leave and run. They asked me if, since I had a lot of experience with germanium detectors, building them and so forth, would I take the responsibility of zone refining? First of all, treating the oxide, reducing it to a metal, zone refining it for Majorana. I know how to do that, and I knew the people in industry that could do that. So we set up a shop off the reservation of the laboratory, because that was too bureaucratic, in near a parking lot right across from Ortec. And so we took the oxide, we reduced it, and then we took the metal and we zone refined it with an RF system. And that RF system was a handmade deal. It's still out at the South Dakota Schools of Mine and Technology, or Cabadan, whatever you call yourselves now. You have it. You have the thing we built. I don't know if we'd use that again, but something similar. And so, so what we did was to zone refine everything, got about a 70% yield, because as things came off the germanium line, we would rezone, and not which was a 99.9% conservation, as opposed to chlorinating it and burning it, doing chemistry, which is 70%. Well, that's where we are now. I spent, I don't, right now, I'm trying to zone refine germanium and other things for, with an electric coils that was made in the Mellon Company. And so I'm not sure whether I will be successful enough, but that's what I plan to do with Legend, if it works. If not, I will try to get the RF building, but RF thing running again, because you can't make detectors, make blanks in Oak Ridge and be shipping the scraps back and forth to Germany. It just won't work. Plus the fact the German company is now not working. So that's what we're trying to do for Legend 1000. And also I'm trying to do, I have been successful in zone refining lithium molybdate for the Cupid or Quarry with particle identification. My only problem is I'm only 2 years before my 90th birthday. And there must be some kind of a, when the guarantee on my life runs out. But at this point, I'm still active, and I still remember so many of you in the work that I've done over the past 55 years here at the University of South Carolina. And I don't intend to quit, but God may have other plans. But I have had a lot of fun. I've known a lot of you people, and I've enjoyed working with you, and even those that I haven't worked with, knowing about your work. It was a serious mistake to get an old guy to talk about the history. Very bad.
Well, I appreciated that, Frank. So thank you very much. And I did ask him to give us a history lesson there. So thank you for your indulgence.
I wish my memory was half as good.
Okay, so
you remember a lot of things that I wish you wouldn't remember there, Eric.
Perhaps.
Okay, so there were a number of questions in the chat. So thank you, Maurice and Jim. So I'll start there a little bit. Susanna, maybe I can start with you and ask you maybe what are the challenges you see moving forward in terms of the science requirements for future production of low background material?
Maybe I mentioned before one of the issues that we have to face in the development of low background materials in general, but in particular for copper, is the difficulty to assess the low levels of activity which are being achieved. And the lower the values, the harder the measurement. So I think that there must be a development in parallel to the techniques to reduce the activities, but also to improve the methods to assay the activity in bulk and on surface, of course. So I think this is one of the challenges for sure.
And do you see any new techniques being required or coming in, or do you really think it's refining, what we have? ICP-MS is, of course, very nice for stable isotopes like uranium.
I'm not. I have not experience at all on ICP-MS, but I think there's a lot of work to to further improve the sensitivity. And I think that it's of course it's possible to rely on this technique to get the required sensitivity. But of course, Eric or anybody else can much better to say on this.
Thank you. Eric, actually, I was going to go to the next question with you. What do you think about industrialization of this process? You've worked a little bit on transferring this to other groups, but I'm sure you've thought about commercialization and industrialization. But.
Yeah, I think, it's actually been attempted a couple of times. Sarco some years did it, some years ago did that, and we're delivering what they called 6/9 copper. But we, of course, at the time didn't have the capability of assaying it to really see what was in there. But they got out of the business because there just wasn't a sustainable demand. And now since then, and still currently doing this, is Mitsubishi. They set up a capability, coming up on, almost 10 years ago now, but and they provide 6/9 copper. We have had a chance to look at that, and of course we haven't assayed a lot of that material, but we were a little bit surprised because it actually, at least from a radio purity standpoint, wasn't as good as what we were getting from Arubis. And it varied quite a bit, just the few samples that we had. So they're still making it. I don't know, I don't have a lot of data, but I would say that, based on that, there apparently is enough demand that they're continuing to do that and have been in that business now for a while. So I think most of their demand, however, is in the electronics industry. So I think going forward, if you were to try and industrialize this, you would have to establish greater demand to make it viable from a business perspective, so it would keep, you keep going forward. And I think that's what Mitsubishi's done. So I think we are still a small player in all of that.
But that would never go underground, right? So you'd still have the cobalt ingrowth problem.
Yeah, that's correct. Right. I mean, you would think that if there were enough demand by this, this part of their business, that they might locate that underground. But right from the start, right from the get-go, they didn't take that on. So in my mind, that's another vote for why we weren't the driver for that. It's because I think they're using them mainly for things like sputtering targets and so on in the electronics industry.
Okay, and then Cabot N, because
could I ask Eric a question, or do we have to come back?
Please go ahead.
Eric, you talked about this a layer of copper on top of a structure. How successful was that? I missed. Is that with respect to getting rid of the alpha background? Because
from the perspective of alpha, it was very successful. We we did some work for News G where we plated the interior of their sphere, but to try and attenuate the lead-2tin contribution in the bulk. But that's not. We laid down about 0.5 millimeter of electrophore material, which is very pure. We assayed that, but you don't get a lot of attenuation with only 0.5 millimeter of copper. So for them, actually, they tried it just to make sure that, to verify that it works. They're still doing those experiments. We'll have yet to see how successful that can be. They had more problems with surface cleaning than anything else.
Well, that's a problem.
Yeah, that's the problem, right? I mean, you can, and Cabanan alluded to this earlier too. You can make this great material, but how you handle it subsequent to that is just as important. It's you know, if you have this wonderful electroform material and you're worried about radon plate out and you leave it sitting out in the room, clearly you're going to have an issue. And so, and that's just one contributor, right? I mean, machining and various handling and so on. I've even found, like, for example, the cleaning technique, and we allude to this in this later publication that I mentioned just this year about this cladding. Implementing the surface cleaning is very technique dependent. And if the polonium is not located right on the surface, so if it's a radon plate out, you've got a very good chance of, of removing the polonium. But if it's sourced from the bulk, so from lead-210 decay in the bulk, it tends to act as an accumulator on that surface as you are dissolving away the surface of that copper. And the reason for that, of course, is that, you know, we have all this copper that's trying to go in solution, so there's plenty of electrons available, donates those to polonium. You can try to get polonium into solution, but with what's available, because of the copper going in solution, the polonium plates right back out, because polonium has a reduction potential that's even higher than that of copper. So if it's in the bulk, very difficult to remove. If it's right on the surface, you can remove it.
Thanks.
Thank you, Eric. Okay, so Cabadan, I wanted to ask you a bit about the students that you see going through this work and you have going through this work. What sort of students do you have working on this low background material chemistry, and what kind of jobs do they get after graduation?
Well, let's see. We've had chemical engineers that have just gone off into typical chemical engineering jobs. But one that was very interesting, we had a chemical engineering student that came in and really did an assessment about the process of the amount of liquid and waste to decommission the temporary clean room. And just in the sense of the process of making sure that recycling was handled properly and just the movement of equipment, writing a decommissioning plan really helped when it came time to applying for a job, which industry, you know, interestingly, he ended up at one of the largest cement manufacturers, and part, I think, of him getting the job was explaining, you know, they asked, are you afraid to get dirty? And he's like, let me tell you about my trip to work and going down into surf and the precautions that have to be taken, and then into basically a large scale chemistry lab and making sure that things stayed clean in the handling and the movement of equipment between where the electroforming was occurring and the Davis campus, which is where the machining was happening. We had a grad student who actually is a pretty high-ranking process chemist developing all the new techniques at Arubis. She actually has gotten a pilot plant funded that they will be building for Arubis through her practice. So she was our PhD student. But then in terms of things like the other undergraduates we've had great success with physics undergraduate students as they go to apply to school. You find that, you know, physics, not to knock on them, but they really lack from the experimental bench chemistry that you would have. You know, they can program and you know, handle electronics, but in terms of things like, you know, the skills that it comes to setting up a lab and understanding hazards and safety, that's something that you really benefit from being in a chemistry lab. So right now, you know, metallurgical engineering, same situation. They tend to have as much lab experience usually as chemists, but just to get the hands-on experience for things like electrodeposition and that type of chemistry is it's very useful for them. And so they're all going out into industry or to graduate school at various locations. But if you have 20 students that all have 4.0s, how is it that you look different, or how do you set yourself apart? And just having the experience of being part of Myrana, even if you weren't a physics student, has been a great benefit to be able to say, understanding clean room, understanding techniques, understanding electronics, and safety. I'm very surprised at how much of an emphasis understanding safe practices and OSHA and all of the things that go along with that. That's something that's very, very favorable when it comes to a recommendation and how students are selected for work in industry or even graduate school.
Thank you. You sort of mentioned this a little bit, but have you seen places where, at least on some of the technical work, that the thought patterns of having that different educational background, that different work background, differences just between physics and chemistry in terms of approaching problems, where you've seen that advantage of this multidisciplinary effort?
I would say they expand it. They usually come in with so limited knowledge that you really just are expanding what is out there and what work is done. The proximity of our university to surf is very unique in the fact that for them to be able to go underground and to see the experiments in the labs, especially at our university, the only involvement from our physics department is actually with LZ or Dune. And so those are, very different experiments, even just in their construction setup. So even if you've had a student that worked on those experiments or know about them, to come to Myrana and to see the difference in the amount of chemical handling and the fact that we're hiding underground, and creating this quiet, clean environment opposed to something like a dark matter experiment is a huge difference.
Thank you. Okay, so Frank, because you seem to have worked with the Office of Naval Research, I'm going to send this next question to you. So how critical do you think the other applications, the national security applications are? And maybe you could say a minute about where some of those students are that you mentioned in terms of what their research activities are on now.
Well, actually, most of it's at PNNL. There are things that the folks out there like Todd Hosbach and Miley and those who can't discuss with me. So I know that it's played a very high level in PNNL has played a very high level in national security, in non-proliferation. Miley is one of the best known people in that area in our country. So that's the spin-off, because that's what Wagman and Brodzinski were doing when I went out there. They weren't interested. They didn't know anything about double beta decay. There were a couple of nuclear chemists getting their PhDs at Purdue and finding a job in nuclear chemistry, and they have it and that's what they fell into, and they were experts. And the Battelle Pacific then was a big player. So I don't know how you knew I was associated with the Naval Research Lab, but I was for many years, for 8 years, not full-time. I was just a part-time naval officer there. And I know that most of that kind of work was not supported by ONR. ONR was supporting things more like the 6.2 and the 6.3 level and beyond, but they would pay to have such things done. So that was mainly Department of Energy, and before that, the Atomic Energy Commission, before the Department of Energy came along. And that's of course in non-proliferation that germanium technology and ultra-low background germanium has played a major role. But I'm not an expert in that because I don't have the clearances and nobody will talk to me about it.
So Eric, maybe you could mention that a little bit as somebody who's built the capability and you're trying to maintain it and grow it. how important has the investment from these other areas, the NNSA, for example, in non-proliferation treaty verification type technologies, how much has that helped sustain the capability at PNNL?
Well, it's really played a critical role. I would say that you know, there were devices that were made prior to Myrana that informed the the Myrana electroforming process. RN Labs or Cascades, you can call it, it's still functioning here at PNNL, which is similar as what Frank mentioned. These are 7 germanium crystal cryostats that are both looking at one another, and there's a sample placed between, so a total of 14 germanium diodes looking at that. And that was made out of electroformed copper, and the processes and our ability to build reliably larger cryostats came from that effort. And this is prior to Myrana. So really, a lot of what we knew going into Myrana was based on some work that we had done for NNSA. Now, then along comes Myrana, right? And we learn a lot from that processing. As Cabadan mentioned, we had 6,000 pounds of copper that we electroformed underground. I think it came out to like 65 different runs, Cabadan, something like that, in these baths. And we gained a lot of experience. So now, we build proportional counters that are used for a variety of things, everything from, age dating groundwater. So we're looking at argon, but, and treaty verification work. So we bounce back and forth between the basic science informing the applied side of things like NNSA, and then our work with NNSA, we have to develop something new there, and we can take that and we apply it back into the research field. So it's a great partnership. It'd be nice if they kind of got together a little better, but it does work.
So I guess that spurred a couple of comments from Maurice here. So could you comment on the scale of Myrana versus NNSA, or is it really like largely majority supported by NNSA and then switches to Myrana at least that's the idea I got from what you just said. But.
Well, the problem with this project-based work that, for example, is like Myrana and other physics experiments is the technology tends to leapfrog. We have a few years where we learn a lot and we do a lot of work, and then suddenly the project, funding and effort fades away. And so, frankly, I think we've seen a model of this in the past where it could be somewhat disastrous. We've seen this in the assay field many years ago. There were people, Greenberg did work in Canada doing copper and lead assays, and it was quite good work years ago. But there wasn't enough work, and they moved on to other things. So they weren't doing any low background assays. And that was a starting point for us when we started developing assays further. But, there was this leapfrog, and we lost the continuity of the individuals involved. And so there's an expense associated with that, of that overhead of reassembling or assembling a new team. And every time that happens, it's costing us time and money. The advantage to the ongoing demand, let's say by NNSA in the production of copper, is that now we have something that's filling that void between projects. So there's Myrana, and Myrana is kind of waxed and waned. And now, at least there's some Legend 200 work, there's NNSA, and then, there'll be the next generation of projects, that come along here, maybe even this year from NP and DOE. And then we'll see the next leapfrog of technology forward. So at least there's something going on in between those projects to help maintain the continuity of the capability. But, if we don't, we really have to be very careful there, because if we don't maintain that, we're going to lose that. And so we have to really look at some way that we tie the projects together a little better.
So either tying the projects together, or it sounds like, there's no base program for chemists within nuclear physics, and that's a challenge, because if there is a gap between projects, that's a real challenge to maintain the capability.
Right. It certainly is, and it's the approach in the past, or even currently, I believe, is that programmatic or base grant funding really goes towards physicists, and then engineers or chemists are project funded. And so I think we have to step back from that model a little bit, because these experiments are getting so big and so multidisciplinary that we have to look at how do we maintain that continuity between capability between big projects, so that we don't lose that when the next big project comes along or the next capability is needed. We don't want to lose that expertise from, one generation to the next, or one project to the next. So I do think we have to step back from that model a little bit and try to figure out what, how do we provide some of that funding so that we maintain the continuity. But I'll also mention that the R&D is becoming more and more difficult, and it's not an R&D project that happens in 6 months. It's an R&D project that takes years. And if we aren't doing that work between projects, then if we're just waiting on project money and waiting to leapfrog every time that project comes in, we don't have much time to do that. We don't have much time to make those improvements. So it's very slow to move us the overall capability forward if we don't have some sort of sustained R&D program.
Okay. And then there was one more from Maurice that I think is probably for you. In terms of the assay, is there also a synergy with NMSA on the assay side?
Oh yeah, absolutely. Our lab that does ICP-MS work supports a lot of other projects, but even just electroforming, for example, we are always doing quality assurance tests for the purity of the electrolyte. We do that for Myrana. We still do that today, and of course, that's supporting a variety of different programs. It's anything from again from the NSA to the basic research project. So just from that alone, the assay is supporting that. But we're looking at a lot of things right now that are not necessarily those, the big three that we are always concerned as far as the basic science work, which is uranium, thorium, and potassium. And so we're doing things like right now for high dynamic range iodine analysis, for example. So when we develop that capability, our ability to keep an extremely low background on that instrument is very important for any trace analysis that we need to do. And we learned that from doing things like developing Myrana assay.
Okay, so I kind of wanted to follow up, well, not on the NNSA stuff, but with maintaining the capability with you, Cabadan, because you're so connected with what's going on at SURF and trying to maintain that capability, improve upon it. You know, do you see some of those same challenges between projects?
Well, right now we are in the unique situation of the fact that, like I had said, you know, that we built the temporary clean room simply as a stopgap because the Davis campus was not complete on time. In fact, you know, it was almost 2 years behind for Myrana to take beneficial occupancy of the space that we were allocated for. And so the nice thing is that, you know, within the Myrana space at Davis campus, there was a lab called the electroforming room that electroforming just did not happen during the duration of Myrana. Now we are electroforming there right now. So when we had to vacate the temporary clean room at the end of Myrana's duration there, the fact that Myrana occupies the space at Davis campus, we just simply slipped in and started electroforming. Now that did cause us to go through a full authorization to proceed again with SURF, which was its own set of headaches and hurdles to jump through. But we, in a sense, consolidated what we already had. We now have electroforming in one room. We have the machine shop that handles the copper in the next, and the detector that houses the wet lab, where all the parts had been cleaned anyway, are now all in one location. So, and all maintained at, you know, they're built as a class 1000 clean room, but we maintain them at less than class 100. So in terms of going forward and seeing that hurdle, you know, Myrana was set to decommission in 2024. That was slid up a year and then another year due to activities with Dune and at SURF. And surprisingly, though, just within the last week, there's been a realignment of priorities at SURF to realize that, you know, the fact that LZ may run for another 5 years and then leave, and Dune is ongoing in terms of excavation, will be a long time out before it's up and running, that Myrana's, not even Myrana, but the capabilities that are contained within the Myrana space are important. And that space is not needed for something else. So for SURF to push us out with nothing to fill that void really is not favorable. So we look at it as we plan to electroform up until the very end, and then not knowing what would happen with Legend 1000, would that move to a different location? We have always planned for something like that, but right now, maybe that capability continues past that date.
Thank you. Susanna, I wanted to ask you a bit about some of the European efforts on copper electroforming. I don't know if you're involved with those, but I know there's work at Modane and Gran Sasso, and even Bolby is talking about it now.
Yeah, indeed. Also in Canfranc, we have a copper electroforming facility, which has produced, for instance, for Anais, small pieces for the enclosures of the photomultipliers. And indeed, the facility is being improved now in order to be able to produce larger pieces and also to increase the production times. And also, I don't know if you know about, there is a very, I think, a very interesting collaboration between Canfranc and Gran Sasso in order to use electroform copper, which is then made powder. And this powder could be used for 3D printing of pieces, which in this way that don't need to be machined. So this project is intended to further improve, of course, the radio purity of specific pieces to be used in the experiments. So the plan is to produce a big amount of copper in electroform copper in Canfranc, then in a company to make the powder, and to move it to Gran Sasso, where they have developed a customized 3D printer in order to produce the pieces. Of course, this is just a project underway. And the idea is to also to assess at the different steps the quality of the material at the different steps of the process. I don't know if you have in the States any similar initiative to print pieces with special copper. I don't know if there is something underway.
I don't know. Have you heard of anything like that, Eric? I think it's actually a really interesting idea, although I think it's very brave to powder it and make that much surface area for your low background material. But I think it's very interesting R&D. Is there anything going on like that in the U.S.?
There's actually a copper consortium in the U.S. that we're involved with, and we've looked at 3D printing of copper. Of course, the big challenge is producing not only copper that's high enough purity that's so finely divided, because the process of doing so, unfortunately, can contaminate the copper beyond what is practical. But then also the subsequent handling, so you have to be very careful. That work, we've had discussions involved. Yeah, it's e-beam, 3D printing capability, and laser capabilities for smaller parts. But we haven't made a lot of steps forward as far as the development of the finely divided copper that we would have to provide for that 3D printing capability. So until somebody steps up and wants to to fund that sort of R&D, I think that's kind of stymied right now for us.
So how far along is that effort in Europe? Have you produced any pieces yet, or?
You mean just electroform pieces? Yes. This project of the 3D printer is just starting, so we have to wait to have the even the very preliminary results. Yeah.
I think I was in Gran Sasso maybe a year ago, and they were unwrapping the 3D printer. Okay. So maybe another question for Frank. After going through that history, and it was sort of organic in terms of how it evolved, looking back, if you were trying to target this directly, which I guess you were, knowing now what you know now and you didn't know then, would you have done it differently?
Yeah, I would have found Eric Hoppe much earlier. No, we didn't have, we didn't have a good chemist like Eric. We had a guy with gut feelings that convinced Ron and I that you could do electroforming of copper. But unfortunately, we did develop we would put a little bit of copper on and then take half of it off, back and forth. Eric has done so much more in developing the technique to be able to produce the kind of copper we had in Majorana. I mean, so I could see that what you really need, we were, all of us that were working on the IJEX that started this, were just amateurs in many of the areas. We could read things that people wrote. Oh, yes, let's try this. And we halfway got there. And we did better than what was done before. But we didn't, Eric made this point too, we didn't have the kind of funding for R&D. We had the kind of pressure is, you think you can do it? Well, yes, we think we can do it. Well, then do it. Not take some time for R&D. And I think right now, I hope, I don't know who's listening, but R&D that was supposed to be put forward for a down selective double beta decay experiments, in my opinion, was just nothing. I mean, Berkeley had $100 and something thousand, and we had to give half of it to Eric so we could get ICP-MS done for the samples that I'm doing. There was not really an effort in trying to do just what you're chasing here. Let's get the technology in order. If it's going to be 2 or 3 years down the road, let's get some money into the R&D. It wasn't done. And I think that Eric made a good point there, that we're just not going to be able to make giant steps. What amazed me is what the Canadians did with snow. I mean, they said, we're going to do this, and they did it, and they put a lot of R&D effort in it, and they made it an impossible experiment go. I mean, most of us that were watching from the outside thought that was not going to be very easy, or if even possible, and they did a beautiful job. If you look at the history of almost any real success, it either was done slowly, or it was done with good R&D and upfront. And that's what I would do, but I'm not sure I could have gotten away with it. That's what Fiordini and I wanted to do. No, they didn't want to do that. They just wanted the experiment now.
Thank you. Susanna, do you see much of a difference in perception and the need of creating your own materials between the dark matter groups and the double beta decay groups, or are these the same people in Europe?
I think we are in the end in the same community, so there's a lot of common effort and to work together in the development of low background materials, copper or any other. So I think in the end, indeed, in many cases, it's the same people who is collaborating in some cases in the same experiment. So I think that the cooperation, at least for this, is great.
And I guess maybe Eric, the same thing on the US side. There's this split in the Office of Science, which, especially when you get down to this science between double beta decay and dark matter, there are so many overlaps in technique, but there's this big split in terms of the funding agency and the communities of people working on it. Do you see that affecting some of the applications of this on the dark matter side in any way?
Well, you really want to get me in trouble, don't you? Well, yes, I mean, absolutely, there's a lot of overlap, and you know, yeah, I mean, it would be great if HEP and NP worked in conjunction with one another, but I don't know how well those two agencies are tied together, even though they're both DOE. I think I would defer this question to others. I see Helmut's here, or Jim. Maybe you guys can speak to that.
So at some level, to me, it's, maybe I'll talk to it, since you invited somebody else to talk to it. There seems to be some challenges, at least culturally, between the two groups. At some level, it seems like the double beta decay groups, the nuclear physics groups in the US, have just accepted this as part of the program, that this is certainly part of the Legend program. Whereas on the dark matter side, it seems like an interesting and probably an enabling technology, but it's more difficult to figure out how to incorporate that into the collaboration. And frankly, they seem to be scared of paying for it too, to write it into the projects, because there is some overhead in terms of, you know, custom produced copper is certainly more expensive than commercially produced copper.
Since you asked me, I guess I will comment from my perspective. One of the differences in the offices is that there is a generic R&D, detector R&D program in high energy physics. And so on many fronts, people look to that to do development. And I can step back to 30,000 feet and say, I look at silicon detectors for Atlas and CMS, and they use Ka-25 to advance their detectors, to advance their electronics outside of the projects and in between the projects. And then huge amounts of money get dumped in during the projects. But really, things are already developed. Nuclear physics just does not have an equivalent program. So any R&D like that has to be, sort of on the back of the projects that are going on, or the pre-R&D for the project that is coming up. There is no base detector R&D funding whatsoever in nuclear physics. And so I think those two communities just reflect that. They just grew up differently. I greatly appreciate the Ka-25 program across many, many disciplines. I mean, we heard this morning about the LAPPDs, right? And there's no way we would have the silicon detectors that we have today and diamond technology and things if it were not for Ka-25 funding those efforts consistently over a very long period of time. So, it would be fantastic if that program existed either across offices or, within each office. And I think in BES and BER, it's also the case that there is not an analog to that. Yet, a lot of those programs are developing. I think silicon and ASICs are really where it crosses all of the programs. But, I think there are a lot of capabilities like this where having that kind of at least low-level base funding is helpful. But again, I think even when we heard about LAPPDs this morning, the premise at the beginning of that program was people with base grants could play. And, it was hard for everybody else. And so you got the big labs like Fermilab and Argonne, who had enough funding to be able to afford to pay people to participate, are the ones that manage to do that. And that doesn't necessarily mean you get the right people. It doesn't necessarily mean you get the chemists and the material scientists, because that's really the physicists' money. And so, the physicists are not so eager to give up their money, rightfully so. And I don't think the chemists would be if you walk in as a physicist and say, give me your base chemistry money because I'm a physicist and I can do great things for you. So I think it's systemic and difficult. And I posed this question, it's probably been 2 or 3 years ago now at a CPAD meeting of, are the offices working on ways to have interdisciplinary cross-office proposal calls? And at the time, Glenn answered, yes, but we don't know how to do it yet. And I think if I asked again, the answer is probably the same. At the governmental level, they can't figure out, it's very difficult. And Jeter, you mentioned this at the beginning, was, Congress is basically telling them how to spend the money, and anything that goes against that's hard to do. And so, it's not obvious how you get past that hurdle.
Okay.
I guess I will add, the BRN that HEP did recently, the basic research needs for detector R&D, if nuclear physics chose to do such a thing, could be very informative to what do they actually need as a field in terms of basic R&D, and what ways can you dream up to fund that or enable that or make that happen. And I think there were some very interesting and creative ideas that came out of that BRN. If people haven't read that report, I would encourage you to do so. It might be prudent for the nuclear physics community to think about, having a similar process.
Jim, one of the things that nuclear physics is during its maturation in the past 30 years went to accelerators, and we are not in that game. So we're just hanging out like on the periphery. And it took a long time for us to convince nuclear physics that neutrinoless double beta decay was worth doing at a large scale. And it had to be the various committees that came together that decided that, not us. We were not able to win that battle. So that we're just poor cousins.
Well, and I think dark matter is the same way in high energy physics to some extent, right?
Yeah, yes, but
they're also dominated by accelerator facilities, but
yeah.
There's enough good science from telescopes and dark matter research that I think it's getting, it's gotten traction.
But I mean, the large xenon detectors are not funded by nuclear physics or high energy, are they? I mean, Elena Aprile in Columbia developed her chamber with money for years and years out of now when particle astrophysics office came on, that was a good that was a good office to work with. I don't know. I know that high energy physics is supporting some dark matter experiments, but for a while there was fellows up there that were not interested in anything that had to do with neutrinos or anything dark matter. Things are getting better culturally, but very, very slowly.
Yeah, I mean, it is things like NSAC and SNOMAS that define the priorities for the field. And so right. the way to get them on the map is to participate strongly. SNOMAS is going on right now. That's where you make your case, and that sticks for 5 to 7 years. So those those long-range decadal planning studies are very, very important.
So dark matter is a very significant component of the HEP program. And just to set the scale, the LZ experiment is a $55 million project that's just about to finish. So these are not entirely small investments. Now coming back to the low backgrounds, KA25 has been supporting R&D into low background technology, as Jim is well aware, at PNNL. It's just not happening at the level that you may wish. It is also, to a large degree, geared at the dark matter, and the dark matter background requirements are not as stringent as the neutrinoless double beta decay requirements. So if NP wants to make headways on that, they need to bite the bullet and invest, just as HEP does.
Well, PNNL was the place for low background long before they were allowed to do any real fundamental physics. So the physicists found PNNL, well, we got background, what do we do with it? And the guys at PNNL knew how to deal with it. That's what brought all that fundamental physics out there, that they had already developed for other purposes, for national defense.
Right, but as Helmut's saying, there's no parallel program in NP right now. Whether you think KA25 is big enough or not, the point is there is an ongoing investment there, and it's not just waiting for the next project to fund it, which is the NP model. It would be nice if the agency, if NP and HEP, had a partnership that leveraged one another's funding. But until that happens, I agree. I think NP has to step forward and has to have something that's ongoing.
Yeah, I mean, at some level, there's a reason why Congress split the two offices. I think it's interesting that it's almost a multidisciplinary collaboration between nuclear physics and high energy physics. The physicists are in a multidisciplinary collaboration almost. One last question, and then I'm going to just have the panelists sort of go through and give any last thoughts that they have. But Eric, I was just going to ask you, are there any synergies with the DOE isotope program that can be exploited or are exploited, especially on assay, coming from Nigel Smith?
Yeah, most certainly. And I will say I'm actually a little surprised by one of them, which was our work to do some microchannel isotope enrichment work in the past. It's unfortunate it wasn't funded for longer than it was, but there was a couple-year period where the expertise that we needed was applied toward that new problem as far as how to have extremely high purity work applied toward an isotope separation problem. So that goes forward on the material side and most definitely on the assay side. Again, the ability to do trace assay has, this is our growth area at PNNL right now. I mean, we have 4 new people starting this year between now and April, just to support our assay side of things. So, and a lot of that is absolutely directed towards assays that are not necessarily the low background community assays, but are just taking advantage of that trace capability.
But Eric, that's not so much the isotope program, right? That's other program.
Right. Yeah. I think the reason we don't apply so much to the isotope program per se is because we're trying to do stable work. We're trying not to do radioactive work, and most of the isotope program is geared towards, radioactive isotopes. That's not to say we haven't done any work in that area. I think that's what keeps it out of our laboratories, because obviously we don't want some of that material coming into our low background area. We do have some of that capability elsewhere, but it's not nearly as trace. And so far, I haven't seen a real need to get for the radioisotope area. I haven't seen the real need to get that down to the trace level that we would for the low background laboratory.
I think some of your separations chemistry certainly has synergies there, but that's.
Yeah. I mean, our isolation of uranium and thorium, for example, from copper was because we brought, I spent 10 years, my first 10 years at PNNL in the category 2 nuclear facility. So I had a lot of partnerships and a lot of things that I had done there. And so when we went to develop that, I called on some of those folks that I worked with in the past when we developed that separation, and we still do that on occasion.
Thank you. Any last thoughts while you're still unmuted? Oh, there you go.
The last thoughts? I don't know. We've covered a lot of territory here. I think we're real close to sort of making our next leapfrog as far as with some of the programs we have going on and with NP because they're funding their next generation, their ton scale work. But unfortunately, that's going to make it a time where it would be really easy for all of us to kind of step back and say, well, okay, we're okay for now and we'll worry about this later, as opposed to what we ought to be doing, which is really look at a long-term program that looks to the end of that and then keeps, to the end of that particular project era and keeps that progress moving forward.
Thank you. Cabidan, the same question for you. Any final thoughts about anything we've discussed today?
No, but I'd like to just echo how difficult it is in terms of the interdisciplinary funding for supporting, these physics projects. I've been really lucky for the fact that I was put on project and have kind of just ridden along with Oak Ridge, but the R&D that we're doing is really not something that is we can go out and get funding from another source without the tie to physics, but yet physics seems to just think that all those advancements will magically come and will be utilized in the physics experiment. So, I look at my university with all the interdisciplinary large grants that are being done, and they are just simply not funded through things like NP or even HEP. They're things that are usually DOD that become more interdisciplinary. So hopefully, maybe with the funding of the next generation large scale experiments, that utilization and seeing the benefit of what we develop coming out of these experiments, maybe it will make it easier to get that type of funding.
Okay, thank you. Frank, any last thoughts about what we've discussed today?
We have discussed many things, and it brought back many memories, but I think Eric has pretty well hit it, and so did Cabadan. We just don't have the kind of R&D preparation funding that we need if we're going to do these big experiments right.
And then Susanna, maybe some final thoughts from you.
Well, I think that as we are going lower and lower in the background of the materials, the improvements are harder. So I think it's very important to cooperate and to share all the new developments and the new techniques, and also for assays. So I think cooperation is very, very important.
I agree. I think it's been an amazing amount of work and an amazing progress, and working together and capturing the amazing chemists that we are able to get their attention, I think, and the amazing physicists. I think we continue to make progress. So thank you all. That's the end of the panel. Thank you to all our panelists again, Eric, Susanna, Frank, and Cabadan.
It's been fun. It's been
Just a
fun.
reminder, tomorrow is a holiday, and we'll resume with the last session on Thursday.
Thank you, Maurice.
Thank you, everyone.
Thank you.